Earth is 4.5 billion years old. Today Earth has mountains, valleys and of course complex life including us. It's hard to imagine what Earth would have been like back when it first formed. Unfortunately, most of the rock record from these early eons has been destroyed by Earth's processes, such as subduction. But some rocks have survived from the Archean that can tell us a lot. Along with studying asteroids, meteorites and even earthquakes on the moon, we can start to piece together an image of what the early Earth looked like from 4.5 billion years ago to 500 million years ago. Strap in as we take you back to the earliest stages of our planet's vast history and discuss what Earth was like before life really kicked off. Let's start at the very start. The solar system is thought to be about 4.6 billion years old. At this time, a cloud of interstellar gas and dust collapsed, caused by some disturbance. NASA thinks this may have been due to a shockwave caused by a nearby exploding star, known as a supernova. When this dust cloud collapsed, it caused a solar nebula, which is a spinning disk of material. Gravity, the force that attracts particles together, pulled more material into clumps that got bigger and bigger. 99% of this material was pulled into the middle of the cloud to form the sun. Once the sun got massive enough, the pressure got so great in the core that hydrogen atoms combined to form helium. So, what happened to the remaining 1% of material? Matter further out also clumped together to form the planets, moons, and other small objects found within the solar system, such as meteors. But why are there 4 rocky planets, and then several huge gas giants? Well, that's due to the way the solar system formed. Only rocky material could survive the tremendous heat that the sun puts out. Materials such as ice, liquid or gas could not persist close to the sun. These materials settled further out to form planets like Jupiter, Saturn, Uranus and Neptune. Earth settled into the rocky terrestrial planets along with Mercury, Venus and Mars. Scientists think Earth formed in 3 distinct stages. Stage 1 is known as accretion, where particles crashed into each other and stuck together due to gravity. As these bits got bigger, they attracted more particles due to gravity. Eventually, this method formed larger and larger bodies. As this occurred, the heavier elements, such as iron, settled down towards the centre of the planet, leading to the creation of the inner core and outer core, the mantle and the crust. During the next stage, it is thought that a protoplanet, about the size of Mars, crashed into the very young Earth. This is thought to have occurred about 4.5 billion years ago. The final stage was a bombardment from asteroids. The common consensus is that these asteroids had significant amounts of water on them. Experiments suggest that 30% of the water on Earth might have come from these asteroids. The early Earth was still very hot, to the point where the entire surface may have been molten. It was unrecognisable from today's Earth. Let's take a trip back to the first eon and see what the conditions were like. The entire 4 billion years before the time of the Cambrian explosion is lumped into one super eon called the Precambrian. Very inventive. The Hadean was the first time period of this eon and began 4.5 billion years ago and spanned 700 million years. If you travelled back to this time period, you would die very fast, as the temperatures would have been unbearable and there was no atmosphere. Because collisions between large bits of rock released a lot of heat, the Earth and other planets would have been molten at the beginning of their histories. Solidification of the molten material into rocks happened as the Earth cooled. The oldest meteorites and lunar rocks are about 4.5 billion years old, but the oldest Earth rocks currently known are 3.8 billion years old. So sometime during the first 800 million years or so of Earth's history, the surface of the Earth changed from liquid to solid. Once solid rock formed, its geological history began. This most likely happened prior to the 3.8 billion years, but hard evidence for this is lacking. Erosion and plate tectonics has probably destroyed all of the solid rocks that were older than 3.8 billion years. The beginning of the rock record that is currently known on Earth is the inception of time known as the Archean. The Archean spans a time period of 1.3 billion years, unimaginable timescales for humans. This eon is so long because historically it left very little record, and there really weren't any obvious extinction events, which is one characteristic that defines the division of geological record later on. I.e., the boring does not show up in a geological record, but it certainly dominates Earth's history. More recent work reveals that much more went on during these eons, and many of these events were literally Earth transforming. When the Archean began, the Earth was up to 3 times as hot as it is now. This meant the mantle was much hotter than it is today. The oldest rocks exposed on Earth from this period are found in Greenland, Siberia, the Canadian Shield and several other places. These rocks include melt sheets, granite, diorites, and layered intrusions. Due to the age of these rocks, they are often heavily metamorphosed, which is where rocks are changed due to heat and pressure. This period was thought to be pretty boring, hence the extremely long times between eons. Even the rocks were pretty stable. Modern plate tectonics hadn't kicked off yet. The mantle was still too hot and bound the continental plates together into a supercontinent. Earth's plate tectonics today are active and have created some of the most recognisable features that we see on Earth. The East African Rift Valley, Marianas Trench, and the Pacific Ring of Fire, to name a few. The plates create the landscape we see today, forming mountains, valleys, volcanoes when they move around. It's almost impossible to imagine what the planet was like before plate tectonics. Geologists can look at the chemical composition of minerals to determine how deep rocks were buried and how hot they got. They found that 2.78 billion years ago, in the late Archean, that the lithosphere, the crusty bit at the surface of the Earth, was very busy. They found supercontinents breaking apart, mountain building events, and metamorphism. Now, this sounds a lot like the plate tectonics of today, but geologists have opinions about whether this counts. It didn't work the same way as modern plate tectonics because the Earth's mantle was so hot. These high temperatures made the crust thin and weak. The limited rock record shows if there was subduction, the subducted crust stayed pretty shallow. This is why some geologists don't think this really counts and is not the first evidence of plate tectonics. However, these early movements may have paved the way for the plates themselves. Plate tectonics likely produced large amounts of continental crust, but the deep ocean of the Archean covered the continent entirely. This early plate tectonics likely produced a large amount of continental crust, but the deep oceans of the Archean probably covered the continent entirely. Only at the end of the Archean did continents likely emerge from the ocean. The emergence of the continents towards the end of the Archean initiated continental weathering that left its mark on the oxygen isotope record by enriching seawater with isotopically light oxygen. It is also thought that asteroid impacts were common and dinosaur-level impacts occurred every 15 million years. Sometime during the Archean eon, the right processes and ingredients came together to form the first life on this planet. Nothing like the life we see today. These were single-celled organisms that lacked a nucleus inside the cell and are quite simplistic in metabolism and structure. Archaea, or their ancestors, were likely among the first organisms that evolved that persist today. One of them, which produces methane as part of its metabolism, can be found in modern environments that are devoid of oxygen, which is toxic to them, and their metabolisms have driven many global biological and chemical cycles. Archaea did not produce oxygen, but other early organisms did. This set up a massive change in how life breathed on this planet, and this also started an entirely new eon. Around 2.5 billion years ago, a new eon started, and the Earth was still a very different place. Pretty much everything was still much more extreme than it is today. The oceans were still inhospitable to most life because of the low oxygen and high sulfur. On land, there was little to no life. Cyanobacteria and possibly lichens had just started to colonize. Even the temperature inside the Earth was hotter than it is today, about 2 times as hot. Geologists have estimated that the world during this time period was kind of boring, with a stable climate, not much geological activity, and the sun was less powerful than it is today. Because the time is so stable, part of it gained the nickname the Boring Billion from geologists, a period from about 1.8 billion years ago to about 800 million years ago. The mantle was still very hot and bound the continental plates together into a supercontinent called Nuna, about 1.8 billion years ago. However, this period set the stage for modern plate tectonics and even the rise of complex life. This eon was still more than 1 billion years before the Cambrian explosion, so other than a few microbes, there was no life on land, and it was all confined to the ocean. The ocean was very different to what it is today and likely devoid of oxygen, but it did have a lot of hydrogen sulfide. This combination of low oxygen and high hydrogen sulfide create conditions that are toxic to eukaryotes. These are organisms that have an enclosed nucleus inside a cell. But prokaryotes, simpler life, made the best they could of this environment. Bacteria and archaea, which are prokaryotes, were happy. Most of the life found in this time was prokaryotic. Due to the sulfur, people think that this time period may have really smelt the stinkiest on Earth. This eon is when eukaryotic life may have started. In China, there is a rock formation that contains fossils dating back to 1.7 billion years ago. So, how did we get from simple-celled organisms to where we are today? Well, life needed a helping hand from the Earth herself. About 750 million years ago, during the breakup of the next supercontinent, Rodinia, A cooled mantle meant rocks weren't sticking together, so separate rock masses could interact, forming subduction zones and mountain ranges. This is thought to be the beginning of modern plate tectonics due to clear evidence of deep subduction, such as metamorphic minerals that could only have formed deep within the Earth's mantle. As this movement occurred, the slabs of rocks fought each other, either smashing together or moving apart. When separation occurs, oceanic ridges form, such as the mid-Atlantic ridge that can be seen in Iceland. In these areas, hot magma is consistently released and forms new oceanic crust. Hydrothermal activity occurs, and with that, massive biodiversity because they are rich in iron and silica, which are important for many life forms. Moving plates also create and destroy habitats, which promotes fast diversity of life. Researchers have shown that biodiversity increases when there are more continents. The continents also affect processes such as oceanic circulation and carbon cycling. The next step we all know about. Life exploded during the Cambrian explosion. We moved through the dinosaurs, 5 mass extinctions, and the rise of the human race, which brings us to today. Earth before complex life was considered a boring place. It was anything but, paving the way for modern plate tectonics, something unique to Earth. And while these plates can be destructive, they were also essential for the advancement of life and pushing us past the microbe stage. If you want to know more about Earth and processes that shape our planet, then you can watch these videos here. Also subscribe and hit the notification bell. Thanks for watching.